So last time we were investigating a new type of a problem, a scattering problem, where now our incoming particle is represented by a packet that comes in and it interacts now with this downward potential step with a potential V naught that's less than zero. The generic behavior we're expecting now is what is called a scattering event, where the wave packet comes in. So here's a sketch of the probability before. I'm drawing that little sketch. It comes in, interacts with that step, and we're expecting now not only the particles to continue on, some of them to be transmitted, but we also expect that some of them will be reflected. And that expectation comes from our general knowledge of wave behavior, where whenever we have this sudden change in propagation properties, we expect in general there to be some type of reflection. In terms of the analysis, we realize that now we have two classically allowed regions. So there are two wave vectors, k1 for region 1, k2 for region 2, that follow the standard formulas that I copied down for you here. I also would like to note, which will be handy for us later, this nice relationship between the wave vectors. If I square them, I get rid of these square roots, and if I do the first one minus the second one, the energy terms cancel, and I'm just left with a positive version of this 2m over h bar squared times v naught, and we just define that conveniently, as we have been, as some q naught squared. By using, then, this idea of analytic continuation, that we don't let it bother us that q naught turns out to be an imaginary number, and we just take over the solution to the upward step, which we had solved properly mathematically for v naught greater than 0. We could simply reinterpret the quantities with appropriate ones becoming imaginary when v naught went to be less than 0, and then we were immediately able to write down the full solution to the time-dependent Schrodinger equation. Our job now, then, is to analyze what these various terms in our solution represent. And already, we should have a pretty good sense from our previous analysis that this first piece must represent the incoming wave. So this piece here and all the associated integration constants that go along with it, I will just call this psi in. That's my inward piece, which would represent the full integral I get when I look at that component. These pieces over here I will call psi sub r, which represents the reflected pieces. We know this will be backward traveling where x is less than 0, so that is clearly tied to this reflected part. So here's my incoming. This is my reflected piece. And now I have something new. In the x greater than 0 region, I have a wave that's traveling to the right. This then would be my transmitted wave, and so I will call the wave function that results from using that piece in the integral as this psi transmitted piece. Now, this is sort of a general scattering problem where we have an incoming wave and then reflected and transmitted waves. There are two broad types of questions we can ask about these waves. We can first ask where and when they appear, as we were doing in our previous example, and we can secondly ask how big are they? In other words, what is the probability contained in the reflected piece? And what is the total transmitted probability? So we will begin again by looking at the time and locations of our packets. Because we've done this before, I hope now that we could do this fairly quickly. So let's begin by looking at the incoming wave. So for the incoming wave, right? It's just literally, actually, if you look at the pieces that we have, this is literally the same incoming wave we had before. We will get the same exact analysis. This is exactly equal to what we had called psi plus in the past, and so we can say immediately then that the maximum location of this incoming packet at any given time t is just the incoming velocity v naught times t. And in case you forgot what v naught was, it's just the incoming momentum, which is h bar k naught, right? That's where all of my k1 components are peaked, right around k naught, right? H bar k naught is the incoming momentum divided by the particle mass, then is the incoming velocity times t. So as I derive these, I will continue with my diagramming I won't go with the storyboards now. I think you understand those pretty well. I will just look at the maximum location of these various components as a function of time t. And my incoming component, as we said, comes in here with some slope of the initial velocity v naught. It then, of course, mathematically continues on into the imagined, the fake mathematical zone. But remember, this solution only applies for x is less than 0, so it simply disappears off the map. Now, how about the reflected piece? This is going to be a little bit different. It comes, again, ultimately from here. Now, when we look at this, notice now I have the same idea. I've got the sharp peak near K naught. So to determine my location, I will be using stationary phase. And I will then be taking a derivative of the phase with respect to K1. But I will evaluate where K1 equals K naught because I have this very sharp peak in my amplitudes. I now look at the phases that I have. Notice that this piece now, because this K2 used to be an I alpha 2, it had some complex phase, but now it's just a real number. There is no phase associated with this component. So there are no phases here. I just have these two phases. I just have the usual minus K1x piece of the phase, and then I have the standard time-dependent pieces of the phase, which are the same as they've always been. Those never change. The only change that's happened here is I've lost any phases from this prefactor, and I have now a minus k instead of a plus k. So taking this derivative then is very straightforward. It just gives me minus x for the first term. This bit gives me the same derivative I've been getting every time. I'll say it one last time, but I don't want to keep re-deriving it, right? Oh, I forgot. It's got a 2m down here in the phase. So when I take its derivative, I'll get h bar. The k squared becomes a k, but the k is evaluated at k naught. The 2 comes down. It kills the 2 in the bottom. So I have h bar k naught over m times t times time t. This, of course, is once again the incoming velocity v naught. I can then solve for x. That then gives me the maximum position for the reflected packet at any time t. And when I move x to this side of my equation, I just get minus v naught t. So indeed, it travels with velocity minus v naught, but now there's no time delay because my prefactor here was real, so it's an instantaneous reflection, and it comes down, of course, with slope minus v naught, and that then is what the reflected packet does. Finally, we can look at the transmitted packet. And this story now will be just a little bit different. So let's go a little bit slowly. Once again, I will be using stationary phase. Once again, I have this sharp peak at K naught. So I will be taking the derivative, and I want the phase to be stationary at K1 equals K naught, right? It's still the phase with respect to K1, simply because K1 is how I'm constructing my superposition. I can then look for other phases. Again, my prefactor now has no phase, so the only phases are in the ik2x and the standard time dependent part. Now the k2x term we have to be a little bit careful about. K2, right, is a function actually of K1. K1 and K2 are not independent of each other. They are interdependent functions. When I change K1, K2 changes its value. So to remind myself of that, I'm going to remember to write K2 as a function of K1. That then is multiplying x, as we see here. And then finally, I've got the usual time-dependent phases, h bar K1 squared over 2m times t. Now the derivative is at first straightforward. It's just a little bit different. Now x is a constant with respect to K1, fine, but instead of just getting x out of here, because K2 depends on K1, I get the derivative of K2. So I'll get dk2 over dk1, and that is, of course, evaluated at K naught, at my incoming velocity, right? Or I should be very specific here because I got K1s, I got K2s. This is evaluated at K1 equals K0. That derivative multiplies x, and then minus, and it's the same derivative I had just done here. I'm not doing it again. That's minus V0 t. So then again, I can solve this equation because this has to equal 0 fairly readily. This gives me the maximum peak location of my transmitted packet and how it depends on time t. That will equal, well, when I solve for x, I have to divide, well, this goes on the other side, so I'll get V0 t. That part is easy. But now there's this extra factor from this new wrinkle that we have. And when I solve for x, the dk2, dk1 goes to the other side of the equation where it flips over and it becomes dk1 divided by dk2. And again, evaluated at k1 equals k0. So I clearly have something now that is traveling at some kind of a different velocity. But notice it still is at location 0 when time t equals 0. So this comes out here, right? But it comes out with a different slope. And that slope now, it comes out with no time delay, a different slope. And that slope is dk1 over dk2 times the incoming velocity. And our job now is to figure out what that velocity would be. So let's look at dk1, dk2. Once we have that, we've answered all of the where and when type questions. So if I look at dk1, dk2, I could, of course, solve for k1 in terms of k2 and think about taking these derivatives. That will work. It will just get me into some messy algebra. There's a nice shortcut. I'd like you to notice here that I've got all of the relationship between K1 and K2. So I can just ask myself, let's imagine there's some small change in K1, right? And if there's a small change in K1, there will be a change in this term, and there'll be a change in the second term, right? And I see how all of these changes relate. So let's remind ourselves of that. So notice that I've got K1 squared minus K2 squared is equal to Q0 squared. And if I think about what happens when there's a small change in K1 and K2, the first term has to change by the derivative of the function, which would be twice K1, times the amount of change in the argument, so times dk1. The change in the next term would be twice K2 times dk2, because that's the change in the, this is the derivative of the second function, the change in its argument. And this last piece, well, as K1 and K2 are changing with each other, Q0, remember, is just related to the step size. That isn't changing at all. That is actually just some constant as K1 and K2 change. So the change in that is 0. Once I have this, then it's pretty straightforward to get the ratio that I need, right? Because I can cancel the 2's very nicely. The difference of these two functions is 0. That means the two functions must be equal to each other. And then from this, I can solve very quickly that dk1 over dk2 must equal. So I bring dk2 down on this side of the equation. That leaves k2 on the top on the other side of the equation. K2, K1. This, of course, is all evaluated at K0. So, what I have then is K2, right, evaluated at K0. So this is telling me the momentum I'm expecting on side 2, given my incoming momentum, then just divide it by my incoming momentum. And as long as I'm calling the K's momentum, let's actually make them real momentum. So we can, of course, take any fraction and multiply by h bar on the top and the bottom. The top then really is the momentum on side 2, and the bottom part is the momentum on side 0. And my final observation is the momentum I expect to see on side 2 is just the mass times the velocity on side 2. This is the mass times the initial velocity, right? So my ratio is just then the velocity I would expect on side 2 from the momentum that I'm expecting through this relationship, which is just basic conservation of energy and classical physics, over the incoming velocity. So when I finally substitute this result in up here, what I have is V2 over V0 times V0 t. The V0s would cancel, and I just have the classically expected velocity v2 times t. So in fact, I get the speed just that I would have hoped. So that's really neat. All of the speeds, notice, for these different packets, they just obey the speeds I would have expected from classical physics. And that's a general lesson that I'd like to emphasize here. Let's put a little box about that. Lesson, the packet velocities, and this actually will occur in general. The packet velocities always follow and this is in the outgoing, this is just for the outgoing scattering states. What happens during the scattering, we are not making any claims about, but for the outgoing scattering states, I should say outgoing, just to be clear, for the outgoing scattering states, match, those velocities always match, they always follow, is what I'm saying, the classical expectation. That's kind of neat. But there's another note I'd like to make. Not in this case, but in general, there could be quantum delay times, right? In this case, there actually weren't any quantum delays. But in general, there could have been. Okay, very good. So we know where and when our packets are in this solution, so we see how those behave. The next big question, of course, is, well, how big are these packets? How much is actually, what fraction of my particles are transmitted and what portion are reflected? Now, remember, the way we would determine that is we want to know, basically, if I'm looking at psi squared, which is what I've been sketching, which is, of course, the probability density, if I want to know the total chance of reflection, I would just integrate from here to add up over all the probability for the particle that actually has been reflected. If you think a little more about that, the best way to evaluate that would be to wait a long time so that these packets are nice and far separated from each other, and then all I have to do is integrate up all of the probability that is in my packet psi r. So let's now consider those reflection probabilities.